Hello everyone! In this video, we'll continue improving our clock by adding a multiplexing circuit as well as a clock divider for the fast clock. I hope you enjoy! So in the past video, we have started the clock module. We have built these three clocks, the fast clock, which is running at 28.32 megahertz, the slow clock, which is a variable frequency clock that goes from around 1 hertz to 1 kilohertz, and the pulse clock, which is just a debounce button. In this video, what we're going to do is we're going to build a multiplexer circuit in order to be able to select between those three clocks, and we'll also work on the frequency divider so that we're able to divide the 28 megahertz down to 1 megahertz. So let's get started. So the first thing I'm going to do is I'm going to add two new buttons to our clock, and those are going to be used to select between the three clocks. The first one is going to be the mode, and that's going to select between the free running clock and the pulse clock. So whether we want the CPU to run or to be paused. And the second button is going to be the speed, and within the free running clock, this is going to select between the slow clock and the fast clock. There you go. So this is just duplicating 3 times the debalancing circuit that we have already made. And then in order to store the selected configuration, we're going to need 2 flip-flops. And so this is going to be the mode flip-flop. So when it's high, we're going to be on the pulse clock, and when it's low, we're going to be on the run clock. And then we need a second one identically, and this one is going to be this speed. And when it's high, we're going to be on the fast clock, and when it's low, we're going to be on the slow clock. There we go. And okay, so now when I press the mode button, this flip-flop is going to toggle between pulse and run. And when I press the speed button, this flip-flop is going to toggle between fast and slow. So technically, these 74HC74 chips have a Schmidt trigger input on the clock, which means we could potentially remove these Schmidt trigger inverters. However, I'm still going to be adding the chip that contains 6 of them, and I don't have any use for them at the moment. So I'm just going to leave them here so that I don't have to remeasure all the components here to match the inputs of the flip-flop. But yeah, you could potentially remove these if you wanted. Okay, so now we have 2 selection bits and 3 inputs to choose from. And so in order to do the selection, we need a multiplexer, and it's going to be a 4-input multiplexer because it uses 2 bits. And for that, I'm going to use a 74HC253, which is a dual 4-to-1 multiplexer. So I'm just going to put this here for now. I'm going to do some cleanup later. This is going to be an HC253. So it needs power and ground. And I also need to add 2 decoupling capacitor, one for the flip-flops and one for the multiplexer. Okay, so you can see that the 74HC253 has 2 separate multiplexers, but they are controlled by the same selection bits. So the second one we're not going to use, so we're going to tie all the inputs high. Then the output enables are active low, so we're going to tie them to ground. The second output is a no connect. And then at the inputs, we're going to put our 3 clocks, our 2 selection bits, and then the output is going to be our final clock. So we can take the output stage here and plug it in directly into the multiplexer. So our 2 input bits are going to be, so first of all, the speed, and second of all, the mode. Now at the inputs, when both selection bits are low, we are on the run clock and on the slow clock. So bit 0 is going to be the slow clock. When the least significant bit is high, that's going to be the fast clock. And then when the most significant bit is high, we're in pulse mode. And that doesn't change based on the least significant bit. So we just have to put the pulse clock twice here. So yeah, so this is how it works. So we're now able to select between our 3 clocks. I'm going to do a bit of cleanup here on the schematic, and then we're going to build it on a breadboard. There we go. Okay, so this is our breadboard where we left off the last time. I'm going to focus on the clock here. And the first thing I'm going to do is I'm going to add a new breadboard. And I need to connect power and ground. There we go. Let me zoom in a little bit so we can see what we're doing. Okay, so the first chip I want to add is the output stage, and I'm going to put it at the end here. So it needs power and ground and a decoupling capacitor. So the inputs at the top I'm not going to use, so I'm just going to tie them high. Then we need to connect pin 6 to pin 2. And then I'm just going to add a LED on the output. So that's pin 5, going to ground. And the input is going to be on pin 3. And pin 1 and 4 is the set and reset, and we need to tie them high. So let me just test this with the pulse clock. We should be able to toggle the clock, and yes, it works. Okay, so now we need to add the multiplexer. So I have here 74HCT253. It needs power and ground and a decoupling capacitor. Now pin 10 to 13 I'm not going to use, that's the second inputs. So I'm going to tie them high. Pin 1 and 15 need to be tied to ground, that's the output enable. Now pin 7 is going to be our output, and so this is going to go into the output of the flip-flop. And then we need to connect our clocks. So that's our pulse clock coming here on input 3 and 4. I'm just going to add a jumper here for pin 4. Then we have our slow clock going into pin 6. And our fast clock is going into pin number 5. And then we have our 2 selection bits. That's going to be pin number 2, which I'm going to tie low for now, and pin number 14, which is going to be tied low for now. Okay, so I just put this in the wrong pin. Okay, now if both the selection bits are low, then we have the slow clock. If the least significant bit, so that's pin 14, is high, we have the fast clock. Of course, we can't really see it on the LED here because it's too fast. And then if both are high, then we have the pulse clock, and we can pulse the clock with the button. And then if the least significant bit is also high here, we're still on the pulse clock. Okay, so this works. Now I'm going to add the 2 new buttons for mode selection. And just for consistency, I'm going to make these resistors the same colors. There we go. So it still works. Now I'm going to wire up the buttons into the Schmidt triggers. And I'm actually going to wire up at the bottom because they need to go down to the multiplexer. Also, before I forget, I need to connect the ground on the other side of the buttons. So this is our first button. Second button. And third button. Let me just check that they work. So this is the first button, works. This is the second, and this is the third. Perfect. So now I'm going to wire the selection bits. And for that I need another flip-flop. So it needs power and ground. And a decoupling capacitor. I'm going to tie the reset and set pins of both flip-flops high. So that's pin 10, 13, 1, and 4. Then, because those are toggle flip-flops, we need to tie the inverted output to the data input. So that's pin 2 and 6, and 8 and 12. So the bit at the bottom is going to be the mode. So we need to tie pin 5 to pin 2 of the multiplexer. The bit at the top is going to be the speed. So we need to connect pin 9 to pin 14 of the multiplexer. And finally, we need to connect the buttons. So the button in the middle is going to be the mode. So it's going to go to pin 3. And then the button on the right is going to be the speed. And so that's going to go to pin 11. And actually, it's going to be better if I switch this to be the right button. So this is everything connected. Now we should be able to switch our clocks. We see that the slow clock is working and that the frequency is divided by 2, which is what we want. I can change the speed by pressing the middle button. So this goes to the fast clock. Of course, we don't really see it on the LED because it's too fast. And I can go back to the slow clock. And I can change the mode by hitting the button on the right. And then I'm into pulse mode and I can pulse the clock manually. Okay, so now that we have the multiplexer done, let's work on the frequency divider for the fast clock. So what I want to do is to be able to divide this clock down from the 28 megahertz all the way down to 2 megahertz. So this will be again divided by 2 by the output stage. And so the range is going to be 14 to 1 megahertz. And for that, it's approximately a division by 16. And so for that, I'm going to use a 4-bit counter, the 74HC193. So let me make a bit of space here so we have the space to work. Just for now, I'll do some cleanup later. Okay, so this is going to allow us to set a number up to 16 divider. And so this is going to go from 28 to 28 divided by 16, which is 1.75. And for that, we're going to need a dip switch. And this is going to go into the inputs of the counter. By using this, we're going to set the range of the counter. So it's an up and down counter. We are going to wire the oscillator to the down input, and it's going to count down from the input that we have set here. So if we think about it, if we set, for example, 7 here as an input, then the counter is going to count down from 7 to 0, so 7, 6, 5, 4, 3, 2, 1, 0. And then when it reaches 0, the borrow output here is going to go low. It's active low because we need to borrow in order to continue the count. So this is going to pull slow when we reach 0. And so it will pull slow once every 8 clock cycle. So that's 7 plus 1. And so we're going to be able to divide the input frequency by 8. So first of all, the borrow output is going to signal us that we need to load in the next clock pulse, because when we reach 0, we want the counter to reset to the value that we have set in the inputs. So that's 7 in our example. And also, the borrow output is going to be our clock pulse, because it's going to pulse once every 8 clock cycles, and so that's our output. The duty cycle of the signal is not going to be great, because it's going to pulse low once every 8 cycle, but the flip-flop that we use as an output stage is going to be able to clean that up. So the other things we need to do is we need to tie the up counter to VCC, and also the active high reset needs to go to ground. The carry output is a no connect, as well as the individual bits of the counter. Now, in order to be able to set the inputs, when the switch is closed, we want this to represent a 1. So we're going to tie all the inputs of the dip switch to VCC. And then when the dip switch is open, we want these inputs to be pulled to ground, as represents a 0. In the schematic, I'm going to use a resistor network, but in the breadboard, I'll use individual resistors. So this is our new fast clock. Let's implement it on the breadboard. So let's start implementing the clock divider. So I have here a 74 HCT193 4-bit counter, which I'm going to put down here. Let me just disconnect this so I have some working space. So it's going to need power and ground and a decoupling capacitor. And then I also have this dip switch, 4-bit dip switch, that I'm going to put right next to it. We need to pull up the up counter, so that's bit number 5. And we need to pull down the clear, and so that's bit number 14. Then we need to connect pin 11 and 13 together, that's the load and the borrow output. Then we need to connect the down counter to our oscillator, so that's bit number 4. And then we need to connect the dip switch. So first we're going to pull up the inputs. And then on the other side, we're going to put 4 resistors. So I have here 4 10K resistors. We're going to use to pull this down to ground. Pin 15 is going to be our least significant bit. So it's going to go to pin 5 of the counter. Pin 1 is going to be the second least significant bit. So it's going to pin number 6. Pin 10 is the third least significant bit. And so this one is going to pin 7 of the dip switch. And then pin 9 is going to pin 8. And that's the most significant bit. And now our output clock is on pin 13. Or pin 11 because they're connected together. So this is it. So let's fire up the oscilloscope and see if we can measure this. So here's power. So the yellow probe is going to be the oscillator, and the blue probe is going to be the output. And actually let's make this the output of the flip-flop of the output stage. So we have the final clock. So right now the output is high because we're on pulse clock. I can pulse it low and high with my button. And if I change the mode, so this is the slow clock. Of course, the trigger is not set up correctly for it to be displayed, but if I change the speed, then we are on the fast clock. There we go. Let me shift this down a bit so we can see a bit more clear what we want. There we go. Okay, so let's test this. So I've just set the divider to 16. So we should see a frequency of 0.8 megahertz. So that's correct. If I set it to 8, we should be seeing double that. So 1.75. That's good. If I set it to 4, we should again see the double of that. So that's 3.5. So that's good. If I set it to 2, we should see the double of that. And so that's 7. However, it doesn't seem to work properly here. With a divider by 2, we should be seeing 7 megahertz. Right now we're seeing 4, and also the duty cycle is not correct. It's 33%. So what's happening here? What's the outputs of the counter? Okay, so the output of the counter is correctly a frequency of 14, which is expected. And I wonder if at 14 megahertz, the downgoing pulse is a bit too short for our 74HC gate here. Because if you think about it, it's going to go down for, I think, half. I'm not sure, but the flip-flop is clearly not registering it properly. So I'm thinking maybe 14 megahertz as an input is maybe too much. Let's try updating this to an AC gate and see if it works. So I have here a 74 AC, 74 flip-flop. Let's see how it looks like. So if I go back to the output here, and now it's much better. So now we're measuring 7 megahertz at the output. And if I bring the divider back to 1, we should see 14 megahertz. Yeah, this is great. So even though in the past video I've said that we might be able to get away with using an HC gate here, it doesn't look like it. I think with the speed of the fast clock at 28 megahertz, it's a bit too much. So I think we're going to have to switch back to the AC gate here. But otherwise it works. So I'm able to set the divider here by changing the dip switch, and I can switch the clock source pretty easily. Let me add back the LED here so we see what's happening. Yeah, so I can switch the clock source pretty easily and set the divider. So that's good. Okay, so I want to go back to our schematic in order to correct it. So the first thing I want to do is I wired this dip switch the wrong way around. We did it correctly on the breadboard intuitively, but here on the schematic it's reversed. So I just flipped it so that the least significant bit is on the right of the dip switch, and that's input A on the counter. So that's correct. The other thing I want to do is I want to go back on the issue we had with the flip-flop, and I want to try to explain it a bit better. Okay, so we're using the borrow output as an output clock. So let's look at how the borrow output works. I have here the datasheet for the 74HC193, and you can see that it says here that the terminal countdown, borrow, in the countdown mode, goes low half a clock period before the maximum count and returns to a high at the maximum count. So what does that mean? Well, if you look in the timing diagram that's just below it, you can see here the behavior of the terminal countdown. When all 4 outputs are 0, it will pulse low for half a clock cycle. And so that's on the second half of the clock cycle here, assuming the clock is this one here. So what happens is this ends up pulsing low for half a clock cycle, which at 28 megahertz is 1 over 28. 0.322 is the frequency of our clock. So times 1,000. That's our clock period. So it's 35 nanosecond total. And so if we divide this by 2, we get 17.65 nanoseconds is the half period where the terminal countdown is going to go low. Now, we had an issue with the flip-flop because if you look at the datasheet of the 74HC74, in the timing requirements, you can see that the pulse direction of the clock input going high or low at 5 volts cannot be lower than 20 nanoseconds. So we were exceeding the frequency in this case. You can also see that because the datasheet gives you the maximum frequency of the clock. And so that's 25 megahertz for this chip. So by feeding in a signal that was pulsing low for 17 nanoseconds, just sometimes didn't register. One solution to this is to switch to an AC gate, which is what I did on the breadboard. If you look at the datasheet for the 74AC74, if you look at the same number, the pulse duration for the clock can be as low as 5 nanoseconds. So this chip is able to register much faster signals. And so this is why the breadboard got fixed. However, I don't think it's the right solution here, because if we look at the datasheet for the counter again, we can also see that for the HC version, the 193 has a maximum frequency across temperature that is 20 megahertz. So the issue could just as well have been with our counter chip. And unfortunately, you cannot find a 74AC193. You can only find it in the HC family. And so we're not able to upgrade this chip to work with our frequency. What I think I'm going to do is I'm going to, for now, stick with the maximum frequency of 20 megahertz. So this requires changing our oscillator. And then the maximum output frequency of our clock module is going to be 10 megahertz. We can revisit later our clock generation when we want to go up to 14 megahertz because we're going to need a new design. So let me go back to the breadboard and do some finishing touches. So let me remove my probes here. And you know what, I think it's actually better if I use the second multiplexer, which is at the top here, so that routing these cables will be easier. So let me make that switch. Okay, and now we have to switch the side of the flip-flop that we're using, because the output is going to be on pin 9 over here. There we go. Let's see if it still works. So right now I'm on the pulse clock. I can change to the slow clock, and I can change the speed to fast clock. Okay, so this still works. So let me switch back to the HC version of the flip-flop. There we go. And now I'm going to replace the oscillator. I have here a 20 megahertz version, which is in a DIP14 format. So I'm going to wire it a bit differently here so that it fits. There we go. Okay, so in this video, we've improved the clock in two ways. We added the multiplexer circuits to be able to select the clock by the two buttons. And we also added a divider on the fast clock so that we're able to divide it down to a bit below 1 megahertz. In the next video, we'll do some further improvements to the clock, mostly adding the halt and break line, making sure that clock switches happen in the right place in the clock cycle, and do a few finishing touches on the clock. So I hope you enjoyed this one. Let me know in the comments if you've got any questions or feedback, and I hope to see you in the next video. Goodbye.